So let's discuss some fluid basics. So before going into the subject of fluid mechanics, let's discuss what is the difference between solid and a fluid, because this distinction is very important later on. So let's see what is a fluid first, and then what is the distinction between solid and a fluid. So a substance which exists in liquid or a gas phase is basically called as a fluid. Liquid or gas phase together is termed as a fluid. So now what is the difference between solid and a fluid? So let's see that difference. Okay, the main distinction basically comes from the fact that from the ability to resist an applied shear. So let's take down first and then I'll explain. Ability to resist an applied shear stress. So we have already seen what is the shear stress in previous lecture. So that tends to change the shape. So the main difference lies in the fact that when you apply an shear stress or a tangential stress, then how does a solid behave and how does a fluid behave? So if you have a solid, say for example a solid block you have taken, and okay, solid block which is fixed say to the bottom. Okay, this is solid. Now if you apply a tangential force which results in a tangential shear, so what happens? It basically, the solid deforms something like this, right? Okay, so under a constant, so when a constant shear force is applied, say you are applying a constant shear force on a solid, it deforms to a certain angle and then it stops, right? So it deforms, basically the shape changes takes place because of an applied shear. Deforms, so it deforms when a constant shear force is applied. Solid deforms uh, okay, deforms for a certain angle, or say for a fixed strain angle, and then eventually stops. This is what happens, right? Eventually stops. So what you can say is that it can resist an applied shear stress by deforming. So solid resists an applied stress by deforming, and the deformation is basically measured by the angle, and that is defined as your shear strain angle or stuff like that. Okay, so mathematically I can say that the shear stress that is acting on a solid is proportional to shear strain. Okay, and the proportionality constant is basically your bulk, your shear modulus actually. So in solid you would have seen that. Okay, this is well known fact. This is what it happens for a solid. Now let's see what happens if you have a fluid. Okay, and here you have a plate, say at the bottom you have a plate. Okay, and you are applying a force F. Okay, this is, you have a liquid. liquid or a fluid, whatever. Okay, basically a fluid. So when you apply a constant shear force, no matter how small the force you are applying, when you apply that on a fluid, what happens is that the fluid layer continuously deforms. So let's see what happens. So fluid layer which is in contact with the plate. So these are your plates. Okay, say the bottom plate is fixed, and in between the two plates you have the fluid. So the fluid layer in contact with the upper plate basically move along with the plate continuously with the velocity of the plate. Okay, so that is what happens. So let's write down fluid layer in contact with the upper plate would move with the velocity of the upper plate. This is what you will observe in real life, right? When you imagine that you are performing the experiment, move with basically the velocity of the plate continuously. Okay, and no matter how small the force is, okay, so even if I apply a small force, the layer of the fluid which is in contact, that will just try to move with the velocity of the plate. Okay, so I can say that fluid deforms continuously. So if you just imagine this line, okay, so it over the period of time, this line, I mean all the fluid particles here, if you're tracking all the fluid particles on this line, those after a period of time will appear something like this. Okay, got it. So a fluid deforms continuously under an applied force, under applied stress, you can say, no matter how small the stress is. So here when I am talking of stress, it means the force, the tangential force by the area on which the force is getting resisted. So that is called your applied stress. Okay, so from research it has been found out that for most of the fluids, the applied shear stress is basically, instead of getting like what we saw in solid, the applied shear stress is proportional to shear strain. Here the applied shear stress is proportional to rate of strain or rate of shear strain rate. Okay, so what it means is, for a solid, when I apply an applied stress of tau, it will give me a strain of shear strain of epsilon. In case of fluid, when I apply a shear stress of tau, basically it imparts a shear strain rate to fluid. So this, when you apply a shear strain rate to a fluid, so it basically strains over a period of time, and that takes place continuously. So that is the difference. And now what, so you might be wondering what happens to the fluid layer just below the top layer. So if you just go down in this way, the velocity of the fluid which is in contact with the bottom plate will be 0, and somewhere in the middle it will have an intermediate velocity, and as you reach the top, the velocity of the fluid layer which is in contact with the top plate will move with the velocity of the top plate. So the fluid velocity decreases with depth. This you can just observe. And why it decreases with depth? Because due to the internal friction between the fluid layers. So later on we'll see this is basically, this property comes in the internal friction that is defined in terms in fluid mechanics, that leads to a very important property of a fluid called viscosity. Lower plate. So two things you have to see: what happens when you apply a shear stress on a solid, what happens when you apply a shear stress on fluid. Well, that's the difference. So let's quickly see the difference between the liquid and the gas. We have seen what is the difference between solid and a fluid, and fluid means both liquid and gas. But then what is the difference between a liquid and a gas? So if you can imagine that, if you take the container, okay, the liquids basically take the shape of the container, whereas the gases, so liquid will take the shape of the container and it forms a free surface, whereas a gas will fill the available space. Okay, so why does this happen? Now if you look at the liquid, the molecules might be something like this, whereas in gases the molecules are far apart, right? So in liquids, you have strong cohesive force. So cohesive force is basically what the one molecule exerts on other molecules, or if you take a single molecule in a liquid, what the net resultant force, what the other molecules exerts on this molecule. So liquids have strong cohesive forces between molecules, and that's the reason where mostly why the volume is relatively constant for liquid, whereas for a gas depends on the available container. Whether you keep it on a small container or a large container, it will occupy the available space, and that's also the reason why the liquid takes the shape of the container, because of the strong cohesive forces present between the molecules. Okay, whereas in gases you have the low cohesive forces, or intermolecular forces are very low, since molecules, why this happens, because molecules are very widely spread. I mean, in fact it's not sincere. Because of the low cohesive forces, the molecules are widely spread and they fill the available space. Okay, so the reason for the second is first, and it fills the available space. So that's the difference between liquid and a gas. Okay, and why one takes the container shape and why one fills the occupied or available space. So because of the cohesive forces that is present between the molecules. Okay, so now we come to a very important point, the no slip condition, what it means. So we are basically going through the basics of fluid mechanics. Okay, so in order to explain you what is no slip condition, let's take a pipe surface, or any hollow pipe, okay, such that the walls are non-porous. So porous is something like your sponge, which has holes, or which allows the liquid to penetrate or liquid to flow. So porous is something like sponge, you can imagine. Okay, so most of the time the surfaces are non-porous or impermeable. Impermeable which does not permit something to pass through it. Impermeable. Okay, so imagine that you have non-porous surface and the liquid is flowing. So it has been observed that all all experimental observations indicate that fluid in motion. So let me just complete writing down and then I'll explain. Comes to a complete stop at the solid surface and zero velocity relative to the surface. Zero velocity relative to the surface. So what it means is, if you have a stationary pipe, a solid surface, okay, and if you have a fluid that is moving, so if you have a stationary solid surface pipe and the fluid is moving, so what all the experiments show that at the surface of the pipe the fluid adjusts itself such that at the surface of the pipe the fluid velocity is zero relative to the surface velocity. So here if I take a stationary pipe, so the pipe velocity is zero, so basically pipe is stationary. So the fluid also when it comes in contact with the surface, its velocity is zero, or it basically takes the same velocity as the surface velocity. So surface is stationary, so the fluid velocity is zero and fluid velocity is zero. So the velocity profile is something like this. At the center you will have the maximum velocity, and so here the velocity will be 0, here the velocity will be 0, and the layer immediately that is immediate to the layer which is in contact will slow down from the velocity from the uniform velocity. See, initially the entire fluid is moving with uniform velocity. Now when it comes in contact with the solid surface, the immediate layer which is in contact with the wall surface, that speed is 0. So this speed of this becomes 0, and all the other layers also slows down, and the effect is felt up to some point, but at the center it has the maximum velocity, and then because the pipe is symmetric, so you can observe that you will have a velocity profile something like this. Okay, so this is basically the no slip condition. So basically the fluid in direct contact will sticks to the surface due to viscous effects. So in a minute we'll see what is viscosity, and hence there is no slip. So slip is basically the relative motion. So that is what it says is, whenever you have a surface, fluid is moving across the surface, all experiment observations point that there is no slip. So this is for a stationary surface. Now imagine an aeroplane, okay, moving in air. So what happens, now here the fluid is stationary, okay, and now when an aeroplane moves with say velocity v, okay, so all the fluid that comes in contact with the outer surface of the aeroplane, so that starts moving, because that shouldn't have any relative motion. So that's what experiment shows. So what happens is that, say the aeroplane is moving with velocity v, so the surface at any point on the aeroplane will be moving forward with the velocity v. So all the fluid here will attend, so all the fluid here, the fluid layer that is immediate to the surface of the aeroplane or surface of anything that moves in a fluid, it also starts moving with the same velocity. So all the immediate fluid layer will have the same velocity as the surface velocity. That's what this no slip condition means. Okay, so you can have a surface stationary and a fluid moving. So when fluid comes in contact with a solid surface, solid stationary surface, its velocity becomes 0. You may have an object moving inside a still air or a still fluid, and then the fluid layer that is in immediate contact to the object that is moving with velocity v. So the fluid layer also comes, or the fluid layer that is in immediate contact with the solid surface also attains a velocity equal to the surface velocity of the object. So in both the cases you have the no slip condition. So let's see what are the consequences of these no slip conditions. Consequence of no slip condition. This is important. Okay, so the first major consequence is no slip condition is basically responsible of formation of boundary layer. Well, for development of velocity profile, or basically development of velocity gradient. Basically the velocity gradient evolves. Okay, I have for development of velocity profile, or I can say the velocity gradient evolves or builds up. Okay, so say you have a surface and a fluid is, say, initially moving with some uniform velocity. So why I have written u infinity is from very far, I mean everywhere velocity is u infinity. So now when it comes in contact with the stationary plate or stationary surface, you can say, then because it's stationary surface, so velocity here has to be 0 because of the no slip condition. And now, so this layer will slow down just the top layer, immediate layer, and so whatever, so here say initially, so you have a fluid here, this comes to 0. Now this basically applies a drag on the fluid layer immediate to it and slows down its speed, slows down the speed of the second layer from u infinity to some value, but a lower value. So like that, this layer slows down speed of the third layer. So like that, if you just draw the velocity profile, it appears something like this. So here the velocity is 0, I mean the velocity is 0 at the contact point, and then the velocity slowly increases until the effect of this plate is felt. Okay, so this is the velocity of fluid layer. Okay, so the layer that sticks to the surface allows the adjacent fluid layer, or slows down the adjacent fluid layer because of the viscous forces or the internal friction that is existing between the fluid layers. Okay, so what is important is the viscous surface. So viscous is nothing but your internal friction between the fluid, internal fluid friction. Okay, so this leads to, so everything started because of the no slip condition. That's why it is being said that it's a consequence of move. So it leads to velocity gradient and that leads to the formation of boundary layer. So this is a starting point to the formation of boundary layer, and the fluid property that is responsible for this is viscosity. Okay, now the second consequence is, okay, so boundary layer is formed. Okay, so what's great about that? The second thing is surface drag. So does the formation of boundary layer leads an impact on the solid surface? Yes, it does, and that comes in the surface drag. So what happens is the fluid exerts a force on the surface because of this formation of boundary layer in the flow direction. So now taking the same plate example, because the fluid has slows down, so what it says is it exerts a drag on the solid on the stationary surface, and the drag is in the formation of in the direction of the flow. So now I need to apply on this stationary plate and a force opposite to the drag that is exerted by the fluid in order to balance this stationary plate, or in order to keep that plate in rest. So this surface drag is very important. Okay, and fluid exerts this in the direction of in the flow direction. So what it means is, so there are two cases here. Let me just explain two cases here. So first is, you have an object, okay, kept in, and the fluid is moving. So because of this, because of the no slip condition, what happens is the fluid exerts a force on the object, and the object starts moving. Okay, so you need to apply a balanced force to keep it stationary, otherwise the fluid will just drag the object in the flow direction. So this is case 1. The second case is, imagine an object is moving. Say an object means it might be a submarine inside the deep sea, or an aeroplane. Okay, so the example for the second case is, the solid object is moving, so it might be in a fluid. Solid object is moving in a fluid. Okay, it might be an aeroplane in still air, or a submarine in deep sea. Okay, so what happens is, because of this no slip condition, okay, so imagine a submarine moving in a deep sea. So now the immediate layer that is in contact attains the surface speed, okay, and that exerts a drag opposite to the velocity direction. So now the submarine has to overcome this drag in order to move forward. Okay, so all this are consequences of the formation of boundary layer, and that comes from the no slip condition. Okay, so two cases. Here it is stationary object kept in fluid. Okay, so always, I mean, the drag that comes. So important property here is, here is the viscosity. So let's see, apart from viscosity, let's see other properties. I mean, let's see viscosity and other properties in the next coming lecture.